Hi, welcome to another edition of Calculus 2. Today we are going to continue our conversation about sequences. We are going to have a series of definitions that we are going to need later on, and there's going to be also a major theorem of interest for each students who are headed toward mathematics. Let's go and explore this topic together. So we are going to have a few more ideas about sequences. Still many of them are borrowed from Calculus 1, specialized to the case of sequences. First of these is an idea you have seen before, referred to as squeeze theorem. The idea is that if you have a sequence that is between two other sequences and they are headed toward a limit, then the one that is in between also gonna share the same limit. So in calculus you had this question perhaps, or this theorem, in the following context. You had perhaps one function, let's call that function f. So maybe you had the function f, and this function f had some limit, and you had some other function, perhaps g, and f and g were sharing the same limit. And the question was, what if somebody is stuck between these two? So there's like this green function, let's call it function h. If a function is stuck between two other functions and they share a limit, then the one that is in the middle also shares the same limit. So exact same thing applies to the case of sequences. What happens here is that instead of a function whose domain is all the numbers, now you have function whose domain is the set of natural numbers. So instead of the whole function, you have essentially this collection of dots, and you have another collection of dots in for this blue one. And the question is, well, if instead of the green curve you have a set of green dots that are stuck between the other two, then, well, if the red and blue are sharing the same limit, then the green is going to share the same thing. The way this is indicated is the following. It says, suppose we have two sequences. So we have a sequence, let's call it an. Let's consider that as taking the place of maybe g, and another sequence bn, which is taking the place of the red one. Suppose these two sequences share a limit, in the sense that the limit of an, when n goes to infinity, the same as the limit of bn as n goes to infinity, and both of them is just equal to L. And suppose this is a smaller one, this is the bigger one, and the third one is in between the two of them. So and an is the lower and the cn is in between, and say bn is on the top. And then limit of cn as n goes to infinity is also L. So that is the case of limit a sequence that is stuck between the other two. Now we don't really need this inequality to be true for all the n's. Rather, we need it to be true for the n's that start from some place onward. That is, whenever we are talking about the limits of sequences, what they do, the first few cases, doesn't really matter. What happens at the tail of the sequence, that is what's going to determine what the limits are going to be and what they are going to do. So we always distinguish, when we are dealing with a sequence, we distinguish between what we call it perhaps the head of the sequence, and what is there after that, which we are going to refer to it as the tail of the sequence. So we have the head of the sequence and the tail of the sequence. In engineering, they might use some other terminology. They might refer to this in certain context as, say, the transient state, perhaps, and the second portion might be referred to as the steady state. That is when you have some concept of a limit or settling of your values of your sequence, your function to a specific value. Then you talk about the steady state portion of your signal or expression and such. So when we are talking about these cases of limits, always keep in mind that what the first few do is not of any consequence as far as the limit is concerned. From what we need is from some place on that inequality must be true, and then we can have the conclusion anyway. Another example of this thing that comes up is in the context of monotonic sequences. So we have another concept here. Let me separate it from here. Another definition. Definition of monotonic. Excuse me. Monotonic sequences refer to sequences that have a certain pattern of either just increasing or decreasing, but not going up and down. So for example, this F, the way I drew it, this is monotonic decreasing. FG here, the way I've drawn it, is monotonic increasing. And the one in the middle in this example that I drew is not monotonic, because sometimes it goes up, sometimes it goes down and such. So the sequences that have a certain ordering to themselves are much easier to investigate than the ones that go up and down all the time, as we might suspect. So we have monotonic sequences. We have two varieties. We have one that's called non-decreasing. This one simply means as you start at the first element of the sequence, the next one is not less than this. It's either the same or bigger, and the next one is same or bigger than the previous one, and so on. And then we have another version of this thing, which is non-increasing. Non-increasing, rather odd terminology to use there, but non-increasing means the first one is the largest one, and then that's bigger than or equal to the second one. It's going to be bigger than or equal to the third one, and so on. Again, just like the previous case, such ordering is typically only significant at the tail of the sequence. Perhaps if the first few are out of order, that does not invalidate most of the theorems that we are going to have I'm going to explain. But just to have a simple description, simply refer to monotonic sequences where all of these entries are in this particular order. Okay, another concept that comes up handy in discussion of sequences is do they keep going? For example, in this case, we noticed that to use a simplified language, we can call it increasing. As this thing is increasing, what does it do? Does it cross any bounds that you have on it and increases beyond any value? Or is there some number that's bigger than all the entry of these things? So again, we have two types of sequences. One is called bounded above. Bounded above means there is a number that's bigger than all the elements of the sequence. So this means there is a number let's call it say m larger than all elements of the sequence. So we write it like this: an is less than or equal to m for all elements of the sequence n. Let me show you what this thing is about. It's a very simple concept, but perhaps the language might overwhelm you, but that's essentially what you get as soon as you branch out from calculus to mathematics. This type of language becomes the overriding concern to make sure everything is expressed very precisely. But the idea is very simple. Let me go and show it to you here. We have seen this thing before. Suppose I look at the sequence, say 2n over n plus 1. These green dots that you see here are values of this thing for different values of n. For example, when n is 1, first value becomes 2 times 1 over 1 plus 1, which is just 1. When n is equal to 2, this becomes 4 over 3, which is almost 1.3 is this point. So these values are represented by these dots, and the red curve is the function itself with all the intermediate values. Well, what's an example of a upper bound? Here, let me play with this thing. You see this, let's look at this dotted line here. We get a sense that this is bigger than all the elements of the sequence here, is higher than all of them. So we call that an upper bound. Well, if I come a little bit lower, I'm still looking at an upper bound. This is still bigger than or taller than all of these things. It's like if you have a roof over your head and you will raise the roof some more, that's still above your head. So the idea of an upper bound is some line such that all the elements of the sequence are below it. As simple as that. So that is idea of a upper bound. So we call m, this number that you had here, an upper bound for the sequence, which write an in curly bracket. Similarly, we have the notion of a bounded below. Bounded below if there is a number n that is less than or equal to all elements of the sequence, we're going to write it n less than or equal to all elements of a sequence an for all n. So when then we say the sequence an is bounded below n, we call n a lower bound of our sequence. Now, there is a concept in calculus 1 when you were talking about limits of functions and such, and it has the notion sometimes is referred to as a supremum. Sometimes it's referred to as the least upper bound. Sometimes this is abbreviated to LUB, so least upper bound, LUB. That is the smallest number that is an upper bound of a sequence. This is smallest number that is an upper bound of a sequence. Again, let's just go ahead and indicate this is a very simple concept, but might take a while to get used to the terminology and such. So we said all these lines are upper bounds for these set of points that I have here. Okay, this is an upper bound, this is an upper bound, this is an upper bound, and so on. But I cannot go too far down. As I come further and further down, my gap to the points becomes less and less. At some point, if I go below that, some elements of the sequence are going to go above this line. Then I cannot say this is an upper bound anymore. So there is a point at which you have to stop. If you go below that, you are not going to be above all the entries of the sequence. It's like when you're building a home, you don't want to make the ceiling so low that somebody's head is going to hit that. So you are going to make sure that the ceiling is going to stay above the height of average person. So the lowest this can go and still be above or at the level of all the elements of the sequence, that is called the supremum, or the least upper bound, or funny language, LUB of the sequence. Okay, so that's what the supremum is. Very simple idea. Next, we have same thing when we want to hold the floor before, underneath a sequence. So another language that is used there is infimum, or perhaps sometimes called highest lower bound, or maybe we call it HLB. That's the largest number that is a lower bound of a sequence. So just to imitate what we had on that page, if I have a sequence like this, well, this is a lower bound for it, assuming that this is below all the points I got here. This looks like an lower bound, another lower bound. As I go up, there is going to be some point at which, if I go above that, I will not going to be a lower bound anymore. Like if I go here, of course, I have some element of my sequence below this line, so that's no longer the kind of line I want. There is a critical point. There's a critical point that separates all these ones that are exceedingly below my sequence from the ones that are going to cross some of them. So this is what we refer to as the infimum, sometimes abbreviated to INF, or variety of other abbreviation. So this is some sort of it's like a floor below your sequence. You want to hold everybody above it, but then you don't want to let anybody to cut through and go below this line. Okay, sorry. There is a very significant major idea in mathematics referred to completeness axiom of real numbers. So again, these are the kind of ideas that you are going to come across if you want to study mathematics seriously. And it says essentially the following, that if you have a set of numbers, a non-empty set of numbers, and then this has an upper bound, then it has the lowest upper or the least upper bound. So if I have a set of points, okay, so I have a sequence, whatever it is, and if I know that there is a line that is above all of them, so let's call this an M, like an upper bound, and you have a sequence down here, then you intuitively feel like that you can take this line and lower it until a critical stage. There is a critical stage that you cannot go below that without cutting through your sequence, having some of them above this line. So what the completeness axiom says, it guarantees for us the existence of this line. We say there is a real number at which all the elements of the sequence are at or below this, and if you lower this, there's going to be somebody that's going to be above that line. Okay, that comes intuitive to us, but in mathematics we have to consider it an axiom to play with that. So this is a crucial property of real numbers. For example, if we take rational numbers and then expect this to be a rational number, this supremum or the least upper bound we talked about, that would not be true. Okay, next we have a major theorem in this section that's called the bounded monotonic sequence theorem. So let me write it. So we have bounded monotonic sequence theorem. Kind of a mouthful, but it says that very intuitive idea. So suppose I have a monotonic sequence. Monotonic, you remember what we said, is either going up or going down. So suppose I have a sequence that is non-decreasing, or simply stated increasing. Okay, so suppose I have a sequence that's going up, and in addition to that it is bounded. So bounded means both bounded above and bounded below. So we are saying that there is a number where this is larger than all the elements of your sequence. What this theorem says is that the sequence is going to converge to a number, and that number is going to be less than or equal to this. So it says the following: if an is monotonic and bounded, then the limit of such a sequence exists So the limit, let's write exist, and it's gonna be less than or equal to any upper bound that you have for your sequence. So this was a description of some of the ideas and terminology and a major theorem in this section. Again, the way we are going to make use of this thing in this course is that we are going to be resting on our intuition of how this thing going to go. But when you go to mathematics, if you want to major in mathematics, you have to make precise use of these statements, and you build on that. And there's going to be a course such as advanced calculus, sometimes called real analysis or something like that, which you take to become a math major. Okay, so we had a bit of a theoretical discussion here. We are going to go back to our typical calculations, and until then, good luck and God bless.